Hi everyone, this is part 2 of our material on decision rules and error correction. So before we get into the heart of the video, I'd like to remind you about the point of this material. Remember, what we have is a code word, say, inside of a code, and we have a sender who's taking this code word and is putting it through a channel. So we've got a channel here. And in this channel, there might be some noise. So this is a noisy channel. And one hopes that at the end of this channel, the code word C will come out again, but it's possible that something different will come out. So let's suppose Z comes out, which is just some string. The receiver who gets Z needs to assign a code word in capital C to this string Z. Now this is done according to something called a decision rule. So the receiver gets string Z, applies some decision rule, and obtains a code word V inside our code capital C. And what we hope is that C and V are identical. If so, then we have success. If not, then we have a mistake. Now, the decision rule that we apply, there are various types of things we could use. In the last video, we talked about a decision rule called the minimum distance rule, where we did the entirely sensible thing of taking this received string Z and looking for a code word V that is as close as possible to Z under the Hamming distance. Now, there are other types of decision rules we could use. We could guess. We could use a magic 8-ball. However, in this video, we're going to discuss a new type of decision rule that involves probability. So as I said a moment ago, we're going to investigate a new type of decision rule based on probability. So we're going to start with an example. Here we have a code consisting of just 2 code words on binary strings of length 3. And we're going to send these code words through a channel that is determined essentially by a binary symmetric channel given here. So the first thing we're going to want to do is write the entries of this new channel matrix, gamma 3. Then we're going to identify which rows of gamma 3 are indexed by code words. And then we're going to use parts A and B to develop and apply a decision rule to received words 101 and 001. Okay, so first of all, before we go on and do all of this stuff, let's see if we can get a feeling for what this gamma 3 thing is. So the input and output alphabet for gamma 3 is going to be binary strings of length 3. So this matrix that corresponds to gamma 3, this channel, is going to have input alphabet, right, with strings of length 3. And output alphabet strings of length 3. And so I'm going to want to know what that number is. And the way we're going to get it is just to simply multiply the entries of the corresponding binary symmetric channel. Okay, so what is this saying? Well, we have an input string here, we have an output string there, and notice that each string is composed of bits. And to get the probability that the output string comes from this given input string, we look first at the probability that y1 comes from input x1. We multiply that by the probability that y2 comes from input x2, and then multiply that in turn by the probability that y3 comes from input x3. So for instance, if we wanted gamma 3 of, say, 1, 0, 1, 1, 0, 0, what would that be? Well, that's first gamma 1, comma 1, right? So that's the probability of output 1 given input 1, and that would be 1 minus e. So that would be 1 minus e there. And then we want the probability of output 0 given input 0. And that, again, would be 1 minus e. And then we want the probability of output 0 given input 1. So there we would have a bit error, and the bit error probability is e. And so this entry of gamma 3 would be 1 minus e squared times e. Okay, here once again we see our example written in much smaller font this time. It allows us a little bit of space to work. So again, we are to write the entries of this channel matrix, gamma 3. So remember, the rows of gamma 3 are indexed by binary strings of length 3, as are the columns. So the rows, these are input strings. So let's just write them down. So they're indexed by 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. So those are the strings that index the rows of this channel matrix, gamma 3. And then, of course, the output strings are also strings of length 3, so we'll write them up here along the top to index the columns. All right, so there we have it. All right, now look, we have 8 rows and 8 columns. So this matrix, gamma 3, is going to have 64 entries. Now it says to write the entries of gamma 3. We are not going to write all of them. We're just going to write some of them. Okay, so let's look at the upper left entry. So this apparently is the probability that input 0, 0, 0 results in output 0, 0, 0. That means on a bit-by-bit basis, that's the probability of input 0 going to output 0, input 0 going to output 0, input 0 going to output 0. And so that's 1 minus e raised to the third power. Right? It's 3 1 minus e's. Now what about here if the input vector or input string is 0, 0, 0 and the output is 0, 0, 1, then again that should be 1 minus e squared. And then we have input 0 to output 1. That's a bit flip, and its probability would be e. and then 0, 1, 0. Again, there's only one bit, the middle bit, that flips. So we have one E and two 1 minus E's. So here now, again, we have two bits that flip. Actually, no, this is something different, right? We have one that stays the same, namely the 0, and then we have two bits that flip. So that means that we've got an E squared for the two bits that flip and a 1 minus E for the bit that stays the same. Okay, here once again, we only have one bit flipping. So that means 1 E and two 1 minus E's. Here we have two bits flipping, so this is an E squared times a 1 minus E. Again, here we have two bits flipping, so this is an E squared times 1 minus E. And now at the end, we have all three bits flipping, so this is an E cubed. Okay, now you can imagine doing this throughout the array. And we're going to go ahead and skip the entire array except for the bottom row. So it might not be a bad idea for you all now to pause the video and see if you can fill in the bottom row on your own. Okay, well, I guess you're back again. Notice here the input string is 111, and the first entry here is where the output string is 000. So we have 3 bit flips in a row, which means we have 3 E's. So this should be E cubed. Here we have 2 bit flips, so this should be an E squared times a 1 minus E. And here we have, again, 2 bit flips. And now where the output is 0, 1, 1, we have 1 bit flip. And then when the output is 1, 0, 0, we have 2 bit flips again. And then when the output is 1, 0, 1, we have a 1 bit flip. And then output 1, 1, 0, we have a 1 bit flip. And then finally, when the input and the output are both 1, 1, 1, we have no bit flip, and so the probability of that is 1 minus E quantity cubed. All right, so that modulo the middle 6 rows, those are the entries of gamma 3. So now we're going to move on to part B, which asks us which rows of gamma 3 are indexed by code words. So remember, our code just consists of these two code words, 0, 0, 0, and 1, 1, 1. So these are the rows that are of interest to us because they are indexed by our code words. Now, finally, we're supposed to use parts A and B to develop and apply a decision rule to these strings 101 and 011. So we're going to imagine now that you are a receiver, and let's suppose you have received this word 101 in transmission, and you know that that came from some code word, and you need to assign a code word to 101. So let's go to the output column, indexed by 101. And what we want to do is find out which of these inputs has the greater probability. Okay? So the only inputs we're interested in are the ones that come from these code words, 0, 0, 0, and 1, 1, 1. So which of these numbers here is largest? Well, at the top we have e squared times 1 minus e, and at the bottom we have e times 1 minus e squared. So here we're told that e is strictly less than 1/2. And when that happens, 1 minus e will be bigger than e is. And so among these two numbers, this 111, or this number here, is bigger. Okay, so that probability is bigger, and therefore I would think that I would select 111 as the code word that I assign to 101. Now, what about 001? So again, we're going to go over to this column, indexed by the output string 001. I have these two probabilities here. And I want to know which one is the highest probability. That is, which one is the most likely. Again, because e is less than 1/2, the larger of those two numbers is this one. And so I would assign the code word 000 to the string 001. Okay, what we did essentially in the previous example is apply something that's called the maximum likelihood rule. Okay, so it's a decision rule framed in terms of probability. It says if word z is received, then we let sigma of z be a code word c for which the probability that output z is received given input c is bigger than or equal to the probability that output z is received given any other code word, c prime. Now, how do you pick out which code word c to use in this maximum likelihood rule? Well, you can get it from the channel matrix, just like we did in the example. So you look at your channel matrix, and you're letting sigma of z, to compute sigma of z, you're going to look for the code word where the entry, the corresponding entry in the zth column of the channel matrix is bigger than any other probability in that column that is indexed by a code word. But we've now been presented with two viable decision rules, the minimum distance rule and the maximum likelihood rule. Now, when presented with a choice, we want to know which one to choose. And what this theorem here is telling us is if the channel that we're using is an extended binary symmetric channel, sort of like what we were using in the last example, then it doesn't matter that the maximum likelihood rule will give the same result as the minimum distance rule. Okay, so here we're going to assume that our bit error probability is less than 1/2 and that it's bigger than 0. If the bit error probability is equal to 0, then it's fairly clear that these two are equivalent. So we're going to assume that there is a non-zero bit error probability. So let's suppose we have a received word z, and we've got two code words c and c prime. And further, let's let the Hamming distance from z to c be equal to I, and from z to c prime be equal to I prime. Now, one thing that we notice is that because e is less than 1/2, this quotient 1 minus e over e is larger than 1. Okay, that is going to be an important fact that we'll use a little bit later. Okay, so now if we take the quotient of these two channel matrix probabilities, right, gamma cz and gamma c prime z, well, what are those? Well, remember that gamma cz is the probability of output z given input c. gamma C prime comma Z is the probability of output Z given input C prime. And we can find those probabilities by multiplying the probabilities of the individual bit flips, right? So because Z and C have distance I between them, we know that Z and C differ by I bit flips. So this probability is going to have an e to the I corresponding to the I bit flips. The remaining slots, the bits do not flip, and the probability there is 1 minus e to the n minus I. Likewise, in the bottom, because the distance from Z to C prime is equal to I prime, I know that Z and C prime differ in I prime slots, meaning that there were I prime bit flips. And so the probability of such a thing is e to the I prime. The remaining slots, n minus I prime of them, they are each of there's no bit flip at all, and the individual probabilities there are 1 minus e. So in total, we have a probability of 1 minus e to the n minus I, contributed by the slots where there is no bit flip. Okay, so we have this expression, and it simplifies to 1 minus e over e to the I prime minus I power. So now for a moment, let's suppose that this distance, the distance from Z to C prime, is bigger than the distance from Z to C. This means that I prime will be bigger than I. And if that's the case, then this exponent is going to be positive. So I have a number bigger than 1 raised to a positive exponent. And so that means that this result here will be bigger than 1 by this series of equations. Now, if this is bigger than 1, if we clear the fraction, that tells us that gamma CZ is bigger than gamma C prime Z. So what does this mean? This means that if you force this to be small, then you're forcing this to be large. And likewise, if you're forcing this to be large, then you're forcing this to be small. And that means that when you apply the minimum distance rule, you should get the same output as if you apply the maximum likelihood rule.